All right, our next theorem that's going to help us is the rational zeros theorem. Let f be a polynomial function of this form here. Notice this form, as we spoke about earlier, we have descending order of exponents, right? We have n minus 1, n minus 2, all the way down to a power of 1. And then a sub 0 has a power of x to the 0, which is just 1. So we don't write x to the 0. If we wanted to, we could, though, and I guess I'll go ahead and write it just to show you what I mean here. But x to the 0 is 1. Anything to the 0 is just equal to 1. So an example, if we had x to the 4th, that would be n, and minus 1 would be 3, so you'd have a power of 3 here. And minus 2 would be 4 minus 2, which is 2, and then we have power 1 and 0. And that's what you see here on C of x. You see a power of 4, 3, 2, 1, and 0, even though we don't write the 1 and the 0. So we want to actually apply this rational zeros theorem there. So it says, let it be a polynomial of this form of degree n is greater than or equal to 1, where each coefficient is an integer. If p over q is a rational zero of f, so we're trying to find rational zeros here, where p over q is written in lowest terms, then p must be a factor of the constant coefficient. So p is going to be a factor of a sub 0, then that's the constant coefficient. And q must be a factor of the leading coefficient a sub n. So it's going to be a factor of the one in the front. So basically we take the factors of our constant and divide them by the factors of a sub n to see all the possible rational zeros. So on the next slide, I have those written out already. So for this polynomial c of x, our a sub n is 3. Okay. Remember that q is a factor of a sub n. So right here, q is equal to plus minus all the factors of 3, which are just 1, 2, and 3. And then p is going to be a factor of the constant. The constant here is negative 24, right? So p is a factor of the constant coefficient. So all the factors of negative 24, we have plus minus 1, 2, 3, 4, 6, 8, 12, and 24. And this is what you don't want to see. You don't want to see multiple factors because that makes this problem a lot longer than it could be if you had less factors. But these are all of our possible p's. These are all of our possible q's. And then we want to divide them. We want to see all the possible rational zeros, so p over q. And so that's what I'm going to do here. I divide p by q. So I have, for instance, 1 over 1, 1 over 2, 1 over 3. That's what I have here, okay? 2 over 1, 2 over 2, and 2 over 3. Those are these three. 3 over 1, 3 over 2, 3 over 3. That's these. 4 over 1, 4 over 2, 4 over 3. That's these. All the way to 24 over 1, 24 over 2, and 24 over 3. And this looks kind of ugly, but we can actually simplify. For example, 1 over 1 is just 1. Okay, the fractions are already reduced here, these two, 1/2 and 1/3. 2 over 1 is 2. 2 over 2 is just 1. 2 over 3 stays. 3 over 1 is 3. All the way down here, 24 over 3 is 8, but we do the same all the way down. And then we can go ahead and get rid of any duplicates. 1 is repeated. We don't need it here. But after we get rid of all the duplicates that we have, these are our possible rational zeros. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Times 2, there's actually 28 possible rational zeros because you can have a positive or negative of any of these. Now, just remember that these are possibilities. These are possibilities. Well, we need to actually test these out to see if they work. And that's where this Descartes' rule of signs that we looked at might help us. for instance, if we're doing this process here, we're going through and checking for our zeros, and we notice that one of our negative numbers is a 0, then we don't need to try any more of the negative ones because we found that there's only one negative real 0. So then we'll be done with all the negative variations, and we just need to test out the positive ones. The other caution here is that these are only going to help you find rational zeros. Numbers like pi or square root of 2 or square root of 3, those irrational numbers, those aren't going to show up on here. But this still helps us to narrow down. So the way that we can test out these zeros is we can use the remainder theorem. If a polynomial f of x is divided by x minus c, then the remainder is f of c. So this will help us find out what the remainder is. And then we need to check using the factor theorem if x minus c is a factor. The factor theorem says that the polynomial x minus c is a factor of the polynomial f of x if and only if f of c is 0. So if we test out these rational zeros, let's say that we pick c equals 3/2, and we run it through c of x, and our answer comes out to 0, then the factor theorem tells us that x minus c is a factor. So x minus 3/2 is a factor, which tells us that 3/2 is a 0. So that's going to help us narrow down some of this and figure out our zeros. So let's go ahead and apply the remainder and factor theorem to our polynomial c of x. We'll practice testing some of our possible rational zeros. We'll start out with positive 1. So we want to test out c equals 1. Well, when I run a negative through c of x, I have c of 1 is equal to negative 50. By the remainder theorem, the remainder when c of x is divided by x minus 1 is negative 50. So this is the remainder theorem here. Well, by the factor theorem, since the remainder is negative 50, x minus 1 is not a factor. Let's try another one of our rational zeros. Let's try positive 3. So we're going to test out c equals 3. Well, c of 3 is equal to 0. So this is our remainder theorem. By the remainder theorem, the remainder when c of x is divided by x minus 3 is 0. Then by the factor theorem, since the remainder is 0, x minus 3 is a factor. We can also say that c equals 3 is a 0. So we have found one of our factors. We also have another example here. We're going to test out c equals negative 2/3. So this is another one of our possible rational roots, negative 2/3. Well, c of negative 2/3 is equal to 0. So our remainder theorem then tells us that the remainder when c of x is divided by x minus negative 2/3 is 0. Then by the factor theorem, since the remainder is 0, x minus negative 2/3 is a factor. So we can also say that c equals negative 2/3 is a 0. So here, if we think back on Descartes' rule of signs, we saw that there were either 3 or 1 positive real zeros. Well, just now we found one positive real zero, which is c equals 3. So there could be 2 more. And we also saw that there is one negative real zero. Well, after doing all of our work, we see that c equals negative 2/3 is the negative real 0. So we're done with the negative rational roots. If we wanted to, we could test all of these out. I've already done the work beforehand on this. I just wanted to show you these examples. But if you're doing it on your own, you might want to test these all out. Or an even smarter way would be that we've already found two factors. I'm going to show you now that we can actually use synthetic division. Since this is a power of 4, well, we only have two more factors, right? We may have two unique factors, or we may have one repeated factor. But we only, we can reduce this down to a quadratic, I guess is what I'm saying here. So I'm going to show you how to use synthetic division to do that so that you don't have to go through all the hassle of testing out all of your other possible positive rational roots. Like I said, we don't have any more negative ones, but all of the positive ones. So let's go ahead and do that.